Welcome back. Today we're diving into the heart of the hydronic system. Quite literally, we're talking about circulators. Just like your heart pumps blood to keep you alive, the circulator moves fluid to keep the building warm. It's a critical component, and getting it right is the difference between a system that hums and one that, well, causes headaches. Technically, these are classified as centrifugal pumps. Here's how they work. Water enters the eye of this spinning impeller. As it spins, it flings the water outward, adding mechanical energy. That water hits the volute, the chamber surrounding the impeller, and that speed is converted into pressure. It's not sucking water in, it's creating a pressure difference that allows upstream pressure to push water in. You'll see a few different designs out there. The most common in residential stuff is the wet rotor circulator. It's cool because the moving parts are actually inside the fluid. No oiling required, and they're super quiet. For larger jobs, you might see 3-piece or 2-piece circulators, where the motor is separate. Those are easier to service without opening the plumbing, but they need a bit more maintenance. Now, here's a rookie mistake you want to avoid. When you mount these things, the shaft usually needs to be horizontal. If you mount it so the motor is hanging down or sticking straight up, you might damage the bearings or trap air. Always check the manufacturer's arrow, but generally, keep that shaft level. If you remember one thing from this lecture, make it this: pump away. You want to place your circulator so it pumps away from the expansion tank. The tank is the point of no pressure change. If you pump away from it, you add pressure to the system. If you pump toward it, you subtract pressure, which can suck air into your vents. Trust me, pump away. Let's talk performance. Every circulator has a pump curve like this. It shows the relationship between how much pressure, or head, it can produce and how much water it can move. Notice the trade-off? High flow means low head, and high head means low flow. You can't have maximums of both at the same time. Now, the pipe system itself fights back. That's the system head loss curve. Friction resists the water flow. Where your pump curve crosses the system curve, that's the magic spot. That is your operating point. That's the actual flow rate you're going to get in the real world. Not all curves are the same. Some are steep, great for high-resistance circuits like radiant floor tubing. Others are flat. These are awesome for zone valve systems because the pressure doesn't change much, even if valves open and close. Matching the curve shape to your application is just as important as the horsepower. What if one pump isn't enough? You can put 2 in series, like a booster. This doubles the head pressure. It's like stacking batteries. But notice, it doesn't double the flow rate. It just gives you more muscle to push through resistance. Alternatively, you can wire them in parallel. This is for when you need a lot of volume. It increases the flow, but it won't double it unless your piping is massive. Also, huge tip, if you do this, you need check valves on each pump so the water doesn't just spin backwards through the one that's turned off. This is where the tech gets cool. Smart circulators use ECMs, electronically commutated motors. They use permanent magnets and microprocessors. They can actually sense what the system is doing and change their speed automatically. They use way less electricity, and they can solve a lot of flow problems on the fly. For example, smart pumps can offer constant differential pressure. Imagine a system with 10 zone valves. As valves close, a normal pump would fight harder and build up pressure. A smart pump just slows down, keeping the pressure steady. It saves energy and stops your pipes from whistling. And then there's the enemy, cavitation. If the pressure at the pump inlet drops too low, the water literally boils at room temperature. It forms vapor bubbles that implode violently. It sounds like gravel rattling in the pipe, and it will chew up a metal impeller in no time. So how do we stop cavitation? Keep the system pressure high enough, keep the temperature reasonable, and like I said before, pump away from the expansion tank. If you starve the pump inlet, you're asking for trouble. Looking ahead, we're seeing microcirculators. These are tiny pumps using as little as 3 watts, like a nightlight. You might see one on every single radiator in the future, replacing big central pumps entirely. It's a completely different way of thinking about moving heat. To wrap up, circulators are the heart of the system. Remember to match the pump curve to your system needs. Always pump away from the expansion tank to maintain pressure. And seriously consider smart pumps. They pay for themselves in energy savings. Thanks for listening.